Hello everyone, welcome to another part of lecture 9 of ROPT 206 Microcontrollers with Lab. In this part of the lecture we are going to discuss about designing the combinational logic circuits, and we will focus on first the hierarchical design, and then we will talk mostly about the technology mapping, and at the end we will talk about the verification. So these are different steps of the combinational logic circuit design in it. So let's see what the hierarchical design is. The aim of the hierarchical design is to control the complexity of the function mapping inputs to the outputs. So we have, let's say we have a function here which maps the inputs to the outputs. And we might have multiple inputs and multiple outputs. And over here we have the function. Basically we have a combinational logic circuit over there, yeah, at the end, over here. So the aim of the hierarchical design is to reduce the complexity of the design. So the circuit that we want to design will be simpler if we use the hierarchical design. Sometimes it is possible to apply the hierarchical design. When we want to do it, we need to decompose the function into smaller pieces, and those pieces are called the blocks. So the main function will be divided into smaller pieces, into a number of those smaller pieces, and each smaller piece is called a block. Then we can decompose each block's function. Each block now has another function indeed, which might be different than the original function. We need to decompose those blocks function into smaller blocks, and we need to repeat this over and over. So let's assume that we have this block over here. We decompose it into smaller ones, and we do it to all the other ones as well, and we keep going on. So even these small blocks that we have here, we'll try to decompose them into even smaller ones. And we continue doing this until we end up at some point where we cannot decompose the block any further. In that case, we will have a primitive block. So that block will be called as a primitive block, and that's the point in which we will stop. So we will not decompose the blocks anymore. We cannot indeed, yeah? That's the end. And then we will put all the blocks, we will have a collection of all the blocks, including the decomposed ones, and that the complete thing will be a hierarchy. So we'll have a hierarchical design. We'll start from the primitive blocks, we'll combine them, we'll end up with some other blocks, we'll combine them, we'll end up with some other layer of blocks, let's say, and at the end, by combining all of them, we'll have the function, the main function that we were going to implement. Okay, so let's see how this happens in practice. Yeah, here we have an example. The example is the 9-input parity tree. The details are shown in the next slide, but the aim here is that we need to design a function which receives 9 inputs, and those inputs are in the form of binary inputs for sure, so they will be either 0 or 1 in terms of the value. Each input will be 0 or 1, 0 or 1, 0 or 1, and this function will give us one output. The aim of this function is for checking the parity, so to determine whether the number of the ones that we have at the input side is odd or even, and based on that the output will be determined. The output will be also either 0 or 1 because it's a binary signal. And now we want to apply this hierarchical design. So as the top level, we have the 9 inputs and 1 output. This is the original function that we have, yeah, in terms of the specification. Now we can decompose this into smaller, let's say, blocks. Let's see how this could be done. So assume that we have these 9 inputs. If we use 3 of the inputs at once, at a time, let's say, and then apply a 3 input parity tree, which will give us, each one of them will give us 3 outputs. So these ones that we have here are in the form of 3 input parity tree or parity check. And then if we apply those 3 outputs that we get from those blocks into the same, let's say, 3-bit or 3 input parity tree, which gives us 1 output, what you see here will work for us as a 9-bit or 9 input parity tree. So what we have in black is the 9 input parity tree. We have decomposed it into 4 3 input or 3-bit parity trees, and you can see them over there. So we have 4 of them, and now for each 3 input parity tree we can decompose them into 2 2-bit exclusive OR functions. So if you consider one 3 input parity tree, so we have 3 inputs, we have the 3 input parity tree. That 3 input parity tree could be implemented in this way. So you can see it over here. If you call the inputs to the parity tree as A0, A1, and A2, and call the output as B0, you can indeed find out the relation between the inputs and the output. So B0 will be in the form of A0 XOR A1 XOR A2, and this could be implemented using 2 XOR gates. So A0, A1, A2, and B0. So this is what we have for the 3 input parity tree. And then for each of the XOR gates that we have here, we already know the relation for the XOR, and each one of them could be indeed replaced or could be implemented using this combination of the NAND gates. We have 4 NAND gates here. Each one of them have 2 inputs, and each exclusive OR gate could be indeed implemented using these gates in this form. Now, this is the point in which we will stop in terms of decomposing the components, because the NAND gate itself cannot be decomposed. It's a building block indeed, yeah? It's a primary gate. So we stop at that point, and we can say that now our hierarchical design is complete. We have the primary block here, which is composed of the 4 NAND gates. Then those blocks, these blocks could be obtained, could be combined with each other in this form. To form the 3 input parity tree as we have here. And inside these blocks we have indeed this combination of the NAND gates, or simply we have the XOR. Okay, and then those 3 input blocks could be combined with each other in this form. 4 of them will be combined with each other in order to obtain the actual function, the 9 input odd function that we are looking for. So that's indeed how we can apply the hierarchical design. That was just an example to show you how the overall procedure works. Another concept that we have is regarding the reusable functions. Whenever it is possible, we try to decompose a complex design into common reusable function blocks. In this way, the function blocks that we have created could be used later. So we place them in libraries in order to use them later. And of course, we need to have them well documented. We need to verify them and document them with details in order to be able to use them in future. But this will make the design procedure much simpler later when you deal with the complex design problems. You just need to have a record of the reusable functions that you have created. Another concept which is important in terms of the design of the combinational logic circuits is the concept of top-down versus bottom-up design. When we have the top-down design, we proceed from an abstract high-level specification to a more and more detailed design by decomposition and successive refinement. So basically, this is what we usually do, yeah? On the other hand, there is the bottom-up design. In the case of bottom-up design, we start with the detailed primitive blocks, then combine them into larger and more complex functional blocks, and then these functional blocks could be combined with each other, and at the end we will have a system which is performing some task. Okay, but what we do in this course usually is the top-down design. So basically we have the problem that we want to solve, we have the big view of the problem, and then we try to find out more details and decompose it into smaller problems and then solve it in that way. Okay, so mostly in this chapter and overall in the course we will use the top-down approach as just mentioned. And usually what for our design we proceed with the top-down to the known building blocks. Okay, so we have some building blocks which are known, and then we cannot decompose them further. We start from the top and then we go down until we arrive there, and then we can say that by kind of combining them we can obtain the functionality that we are looking for. All right, now let's go into more details of one steps of the design procedure, which is called the technology mapping. For the technology mapping, we are going to consider two cases: mapping to the NAND gates and mapping to the NOR gates. First, we start with the NAND gates. When we want to map to the NAND gates, we have some assumptions. We assume that the gate loading and delays are ignored, so we don't consider them for now. And our cell library contains an inverter, so we'll have access to the inverter, and n input NAND gates, where n could be equal to 2, 3, and so on and so forth. And we also assume that the AND or inverter schematic for the circuit is available. So we start from that point. And then for the mapping, we will do it in this way. We will replace the AND and the OR symbols with their equivalent NAND gates. And then we will push the inverters through circuit fan-out points. And at the end, we will cancel the inverter pairs. So if you have two inverters, one after the other, this will be equivalent to just a wire, yeah, a connection. Okay, so now let's see how we can replace the AND and OR gates with their equivalent NAND. Here you can see it, assuming that we have an AND gate here with a given number of the inputs, we can easily replace it with a NAND gate followed by an inverter. So for the AND, it's quite straightforward. If we have the AND in this way, we can place two inverters one after the other one after that, and we know that AND and invert is equivalent to the NAND. So we will have NAND followed by an inverter in this form. On the other hand, for the OR gate, we can do it in this form. If you have the OR gate with a given number of inputs, we can replace it with a NAND gate and add inverters at the input side. And it's indeed obtained following this. If we have the OR gate like this, I assume 2 inputs for now, we can add 2 inverters one after the other one for each input, and we know that these are equivalent to each other because 2 inverters one after the other one will cancel each other's effect. And then we know that this invert and OR combination is indeed the NAND gate. So we will have inverters at the input side and then the NAND gate. Okay, so in this way we can replace the OR gate with its equivalent NAND gate with inverters. We need to do this for all the AND and OR gates in our circuit schematic. So we do that, and then we will repeat the following pair of actions until there is at most one inverter between different gates. So we will have a circuit input or deriving NAND gate output. There will be only one inverter in between these two and attached NAND gate inputs. So let's see how this is done. If we have 2 inverters one after the other one in series with each other, we will replace them with this simple wire or simple connection. If we have an inverter which provides signal to multiple branches, we can move that inverter after the branch point. If we do so, we need to repeat that inverter in all those branches. Because at the end, what we need to have is to have the same signal here and there, or here and there, or here and there. So at each branch, we need to have the same signal. Therefore, if we want to push the inverter towards the right side of a connection point, of a branch point, we need to repeat the inverter on the right hand side. So in this way, we will be able to combine the inverters with each other, and at the end we will end up with the minimum number of the NAND gates, minimum number of the inverters, and only the NAND gates will be left. Let's see this example here. We have a function which is implemented using some AND gates, 1 OR gate, and 2 inverters. The first step would be to replace the AND gates and the OR gate with their equivalent NAND gates. So you can see it over here. This is what we have for the first AND gate, second AND gate, third AND gate, and also for the OR gate over here. So once we have that, we need to now to combine the inverters. Inverter number 5, which is over here, this could be moved. So we just remove it from there and move it to here and here. Let me use a darker color. And we have the NAND still here, yeah. So you can also see it here. So 5 is here, 5 is there. Then this 5 and 7 will be in series with each other. Therefore, they will be cancelled. They will cancel each other's effect. We will have inverter number 5 here. That 5 will be in series with 6. Therefore, 5 and 6 will cancel each other as well, similar to the case of 5 and 7. We will not have it there anymore. And also you can see that here we have the inverter number 1 and number 2 are in series, they will be cancelled. 3 and 4 will be also cancelled, and the rest will remain over there. And therefore the final circuit schematic that we will get for the function f will look like this. And here you can see that we are using only the NAND gates with 2 inputs in this case, and the 2 inputs here and 4 inputs here for the output gate with 2 inverters. So we are done with the technology mapping in this case. So that's how we do the technology mapping to the NAND gates. Now we are going to see how we can do the mapping to the NOR gates only. The assumptions will be similar to the previous case. We assume that the gate loading and delay are ignored, and our cell library contains an inverter, and this time n input NOR gates, where n will be equal to 2, 3, and so on and so forth. And again, we assume that the AND or inverter schematic for the circuit is already available. The steps for the mapping are similar. We will replace the AND and OR symbols with their equivalent NOR gates, and then we will push inverters through the circuit fan-out points and cancel the inverter pairs. Here you can see how the replacement of the AND gates with their equivalent NOR gates are performed. If we have an AND gate with 2 inputs, as you can see here, we can replace that by placing 2 inverters one after the other one at the input side and the AND gate. And then we know that the combination of the inverters and the AND will be equivalent to the NOR gate. So we will end up with 2 inverters at the input side and the NOR gate at the output side. Therefore, the AND gate will be replaced with this equivalent inverter and the NOR. For the OR gate, it's straightforward. For the OR gate, we can just simply add 2 inverters one after the other one at the output side, and this will be equivalent to the NOR gate followed by an inverter. So that's how we just replace the AND and OR gates with their equivalent NOR gates. And then we will repeat the 2 actions that we have here until there is at most 1 inverter. We will repeat these indeed actions until there is at most 1 inverter between a circuit input or driving the NAND gate output and the attached NAND gate inputs. Let's see how we can do it. So basically this step will be the same as what we were doing for the NAND mapping. Here we have the same example for the NOR mapping this time. The circuit schematic is provided. In part B of the figure, you can see that each AND gate and the OR gate are replaced by their equivalent NOR gates. And then the inverters, wherever possible, are pushed in order to obtain a simpler indeed implementation. You can see that inverter number 1 over here is pushed, and it appeared before inverter number 2 and inverter number 3, so they will cancel each other, and as a result there will be no inverter at the input side of this pin of the NOR gate, and you can see that it is the case here, and also at the first input of the NOR gate over here, and you can see that it is the case again here. And also this inverter will cancel this inverter, and as a result at the second input of this NOR gate there will be no inverter, and that is the case here. And the other inverters will remain in their place. So the final indeed implementation that we have for the circuit will look like this. We have only the NOR gates and the inverters. Alright, so next step for us in designing the combinational logic circuits is the verification. The verification shows that the final circuit that we have designed implements the original specification. So basically at the end of your design, you need to verify that what you have designed performs what it is supposed to do. There are some simple indeed verification approaches which could be done referring to the specification that we had. So we can refer to the specifications in the form of truth tables. So initially we had the specification in the form of truth table. Once we are done with the design of the circuit, we can obtain the truth table for the designed circuit and then compare these two with each other. In terms of the Boolean equations, we may also have received the specifications, or maybe in the form of HTL code. Something important over here is that if what we have here as the truth table or Boolean equations or HTL code, if they are the result of the formulation which is obtained by the designer and they are not the original specifications, then it's quite critical that the formulation process be flawless for the verification to be valid. If you make mistakes in the formulation step and at the end after designing the circuit you just compare it with what you had in the formulation, then you will be fine with the verification, but at the end the circuit will not perform what it is supposed to. So if we don't receive the truth tables, Boolean equations or HTL code from the specification, but we obtain them by formulation, we need to pay extra attention to the formulation step. As for the verification methods, we have two basic verification approaches. One is called the manual logic analysis and the other one is the simulation. When we deal with the manual logic analysis, we need to find the truth table or the Boolean equations for the final circuit which is designed. So you design the circuit, you end up with the design, you find out the truth table or the Boolean equations for that circuit. And then we need to compare that final circuit truth table with the specified one. So we refer to the specifications again, and then we compare what we had there with what we have obtained at the end. And if those two are the same, then we are fine in terms of the verification. If they are not the same, then we need to go back and find out where we have made a mistake. So we need to show that the Boolean equations for the final circuit are also equal to the specified Boolean equations if we have received them in that form. In the form of simulation, the verification will be performed in this way. We need to simulate the final circuit that we have designed, and then the specified truth table indeed or equations or HTL description using the test input values which fully validate the correctness. Then the obvious test for the combinational circuit will be the application of all possible care input combinations from the specification. So we will simulate the circuit that we have, the combinational logic circuit. We will apply the inputs, all possible care input combinations, and then we will observe the outputs. If those outputs are what we should have, referring to the specification at the beginning that we had, then we are fine. If they don't match, then it means that there are issues. Let's go through an example here for the verification. First, we will do the manual analysis. Let's say that we have the BCD to XS3 code converter. It's an example from the previous part of the same lecture indeed. We need to find the SOP sum of products Boolean equations from the final circuit that we already have designed, and then find the truth table from those equations. We can form the truth table and compare the truth table to the formulation truth table that we had. We already have the Boolean equations. For T1 we have C or D, and for W, X, Y, and Z we have the formulas, the expressions. Then we can obtain the truth table. Okay, so if we have A, B, C, and D for the inputs for W, X, Y, and Z, we obtain the truth table for the XS3 circuit that we had, And then we compare these with the original specification. And if you do so, you will see that they match each other. You can just put those two on top of each other and you will end up with the same thing. So in this case, the manual analysis that we have made here verifies that our design is correct. So we have obtained what we were looking for. Now let's go through the simulation verification method. The simulation procedure is like this. We need to use a schematic editor or text editor in order to enter a gate level representation of the final circuit. So basically what we have designed, maybe manually on paper, we need to enter this into the simulation environment. Then we need to use a waveform editor or text editor to enter a test consisting of a sequence of input combinations to be applied to the circuit. So basically, first we simulate the circuit itself, whatever we have here, we simulate it in the environment of the software. Then we prepare the inputs. We need to prepare a sequence of input combinations to be applied to the circuit. Then we apply them, we obtain the outputs, and then we compare them to see with the actual signals that we should have from the specifications, and then we verify that our design is correct or not. So the test signal should guarantee the correctness of the circuit if the simulated responses to it are correct. So if the simulated responses to the test are correct, then we will have our circuit verified. If we don't manage to apply all possible care input combinations, so we need to check indeed for all these possible care input combinations when we want to apply the input. If we don't do that, we might miss some of the care input combinations for which the output is not correct. In that case, our verification might not be done properly. So we need to keep that in mind. Over here, you can see an example of how the verification is done using the simulation. The BCD2X3 code converter circuit schematic is shown here, and it is already entered into the simulation environment. You can see that we have the inverter gates, the NAND gates with 2 inputs, the NOR gate with 2 inputs, NAND gate with 3 inputs, and so on and so forth. And over here we have the AND and the NOR gates together, which gives us the AOI, for which you don't have a single symbol, so they are shown in this way. Then for the input combination, we have A, B, C, and D as the inputs. For this, we need to have all the combination, all the care, let's say, all possible care combinations of the inputs. And you can see that we have them here. So over here for this part, we have all the A, B, C, and D equal to 0. So they are all equal to 0, 0, 0. This means that we have decimal 0. Then in the next part, we have 0, 0, 0, 1. We have the decimal 1. Then later here we have 0, 0, 1, 0. So we have decimal 2, decimal 3, 4, 5, 6, 7, 8, 9, and then back to 0. So you see that all possible indeed care cases are considered. The cases which might correspond to decimal value of 10, 11, 12, and so on and so forth are not considered here because those are not important. Yeah, we don't care about them. So this sequence of the input signals is generated and then it is applied to the circuit, and the output signals here are generated. And now if we check the output signals for each one of those values, for example for input combination equal to 0 decimal, we have here 0011. So for 0, we have obtained 0011, for example. If you check this for all the other decimal numbers, you will see that the verification that we have here is indeed done properly. First of all, in simulation, the output signals here are obtained by running the simulation indeed, and it verifies that our circuit designed in a proper way. So we are done with the verification of the circuit design as well. Alright, so I think that's all for this lecture. Thank you for watching and see you later in another lecture. Bye for now.